Okay, let's talk now about the Android security architecture and how we actually have applications run on Android phones securely. So one thing to keep in mind about Android is that everything is based on the Linux operating system. So this means that if we have a command line interface into our Android phone, it can actually take commands just like any Linux device. So you have your basic commands like ls for listing the file system, cd to change directories, rm to remove files, etc. If you're not familiar with the Linux basics, I would definitely recommend that you get a Try Hack Me account and do their Linux basics room, because that will definitely get you up to speed on how you can do some basic Linux commands. We will be using that throughout the course because we can actually get a shell into our Android phone. We'll be able to do Linux commands on our Android phone, so definitely if you don't know anything about Linux, I recommend going out there and learning something before you go further in this course. So something to keep in mind about Android being based on the Linux operating system is that the permissions to folders and applications are going to be dependent on the Linux operating system file permissions model. Maybe you are familiar with this, where you have 10 different digits that determine information for permissions about files in the Linux operating system. The first digit, as you can see in the picture here, is the file type, and that is going to be a file like a directory or an executable file indicated by a D for directory or X for an executable file. The next thing is that we're going to be defining the permissions of the owner of that file. As you can see in this picture where we're listing the file, the owner has a read and write permission, which is indicated by RW. The next group of permissions is for the actual group, and you can see here that this one is just R for read, and then the final set of 3 is for the other user's permissions, and here it is also read. So the thing that's important about this is that our applications are actually going to be isolated from each other by using this file permission model. So you're going to want to keep this in mind when we talk a little bit more about how this actually affects the real applications on the Android phone. Now, every application on the Android emulator or an Android phone is actually run in a virtual machine known as the Android runtime. Now you may hear this term called a Dalvik virtual machine, and this was actually the very first runtime virtual machine for the Android operating system. In some cases, this is actually still referred to as Dalvik bytecode when we talk about how an application is decompiled into its source code and into machine code. But the Dalvik virtual machine is no longer utilized in the modern Android operating system, has been replaced by this thing called the Android runtime. Now the Android runtime is basically a modern translation layer from the application's bytecode to the device instructions. So you think about it that way, every application has something that it's doing to the device, right? Maybe it's accessing the camera, maybe it's interacting with the device in a certain way, waiting for an input from the user. The Android runtime is how that information is translated to actual actions on the device. Every single application in an Android phone runs in its own sandbox virtual machine. And so every application is actually assigned its own folder with its own owner, which we'll get to in the next slide, which allows the applications to be sandboxed from each other. So they're not allowed to, by default, interact with each other. So in the file system, applications are isolated by creating a brand new user account unique for that individual application. And this is kind of what it looks like from an identity and access management perspective. So each application has its own user for that application. And the user is the owner of the application directory. And that user that is created for the application, that's also the owner of the application's directory, is assigned a UID between 10,000 and 999,999, which translates to a username, usually something pretty similar to like U0 underscore A188 for a UID corresponding to 10188, if that makes sense. Now here in the middle of the slide, I have 4 different directories, and what I'm trying to show here is that these two different applications, one named example.app and another named example2.app, would have completely separate directories. So the top bullet point here, we have our /data/app/com.example.app. This is where our generic application data will be stored for an application called, say, example app. Now the fourth bullet point there, we have the data.com example2.app. This is a totally separate directory owned by a different user with a different UID that would be installed on the same phone. So this is how these two example applications, example app 1 and example app 2, would be installed as their own separate directories. Now, with that said, any given application will also have some additional directories. Like I'm showing in the top 3 bullet points, these are all the directories that would apply to the application named com.example.app. So, for example, the /data/datacom.example.app, this is where the runtime storage of the application will be stored. And also, if we're externally storing any information, we could find that kind of data in Mount SD card, Android data, com.example.app as an example. So that's where we would store externally located data as well. Now, those directories would also correspond with example2.app accordingly, but they would be owned by the same application user who corresponds to the example2.app. So because every single application is assigned its own directory with its own user account, that's the owner of that directory, it stops applications from interacting with each other unless explicitly granted permissions. And how a developer usually will grant permissions to an application to share some data is either through a content provider or a broadcast receiver. As I'm showing in the bottom right hand corner, we have the open with Chrome or Firefox pop up here. This is when we would be using a broadcast receiver to receive some data to the Chrome and Firefox web browsers. Maybe it's like a URL or a website you're navigating to. Those applications would be exposing a broadcast receiver and waiting for that application data to come across to them so they can open up and do whatever they need to do. Now, a content provider is similar to a broadcast receiver, but instead of waiting for a response, our application is actually serving some type of data out to other applications if that content provider is exported. Now, something else to keep in mind about these Android phones and Android identity access management in general is that the root user and system level accounts are really the only way that we're going to be able to get access to all of these different type of directories, right? Like I said, every single application has its own directory owned by its own special user, right? So we need like a sweeping access to be able to access all of those directories because each one has a different owner, right? So that's why sometimes having a rooted device such as we'll be showing in this course with emulators, will allow us to gain access to different application directories and have access to every application directory on the device. Now, an important caveat there is that emulators with non-Google Play APIs will allow root. We'll understand this when we get to the actual emulator setup video, where I'll explain the different types of emulators you should have so that you have some emulators with root access, so you'll be able to go in and actually look at all the application directories. Now, some other just interesting things about Android Identity Access Management that is kind of upcoming things is instances such as profiles, and this can allow you to separate not only application data, but it can also allow you to separate functions such as the clipboard or contacts and cameras into their own separate profiles. So a profile is usually used in use cases when we need something like a bring your own device. Maybe you have something like a phone with a work profile on it and a personal profile, and you want to isolate those two things from each other. So the cool thing about profiles is they still have access to system level functions such as Wi-Fi, Bluetooth, 4G, LTE, obviously, right? But they can also have some isolated aspects. So for example, if you have Microsoft Teams installed on your phone, on your work profile, maybe you do not want to allow exfiltration of data out of there by the clipboard. So you can have totally separate clipboards for the two different types of profiles. Some other interesting things to keep in mind about the Android Identity Access Management practices there's this cool thing called the primary user, and this is actually a user that is first created when the phone is started. And this user is actually always running in the background, and it can only be removed by factory reset. Not necessarily something we'll be taking advantage of in this course, but it is something interesting to know about how user accounts are assigned when the phone is first booted up. You can also have secondary users who are additional users you can add to the device, and those users can only be created and deleted by the primary user. And likewise, you can also have guest users, so you can have a guest user on your device, a fast way to give someone access to your phone and maybe limit what they have access to. Obviously, when we're talking about device security, something important for a lot of parents out there is things like kid mode, right? To isolate what kids are allowed to get access to. Things like Google Kids Spaces, which is currently only on tablets only, but I'm sure it will be supporting additional Android devices. You can also set up things for profiles for kids, and also you can use vendor-specific kid modes, such as Samsung Kid Mode, or there's also some applications out there that will gain full access to the device to allow only certain websites for kids, or to have a time-limited amount of time that kids are allowed to use certain applications. Things like NetNanny and like Norton Kid can be useful applications for parents out there if you're looking at things for kid mode. Now moving into the Android architecture. And this is where we're going to get into the real depths of all the different aspects of Android. We're going to do this based on this diagram here that I took from the Mobile Pen Testing Kit book. We're going to start from the bottom with the Linux kernel. Move up to the hardware abstraction layer, go into the libraries there, which come in two different varieties, native C or the Android runtime. Then we'll go to the Java API framework, and finally finish up with the system apps. Okay, so obviously Android is based on the Linux kernel, and back in November of 2012, that is the introduction of SELinux, which is Security Enhanced Linux. If you don't know anything about Security Enhanced Linux, I definitely recommend going out there and reading up about that, and that was not enabled by default until July 2013 with API level 18, so something to consider when we're looking back at previous versions of Android there. You can see that the Android runtime was now used by default in November of 2014, and obviously they've been making tons of improvements to Android over time. Just some interesting versions of Android to know about, and obviously you can tell from this picture that depending on which version of Android operating system that we're supporting with our application, it can actually determine some of the security vulnerabilities that we might find. And so a common attack path that we'll be using throughout this course is running our application, for example, on API level 29 and maybe on API level 22 as well, to see the differences in terms of the security, to see if the application is doing something different depending on the API version. Obviously, something important to keep in mind when it comes to the Linux kernel is that Android devices have to support multiple CPU architectures, such as ARM, system on chips, 32 and 64-bit chips, right? And applications are explicitly told which version of the Android runtime version to run on. So in our Android manifest.xml, when we get to static analysis, we'll be talking about the min SDK version, and that determines what versions of the Android API or Android operating system our application can run on. Obviously, from a security perspective, based on that Linux kernel picture I just showed, the higher the API version, the better from a security perspective, because we're building on the experience of the Android operating system, right? But the handoff there is that developers always want to try to include the most customers possible. So if we allowed an application to run on, say, Android runtime version 1 all the way up to the most recent version, we'd be including 100% of the marketplace, right? But the downside of that is that that can include some security vulnerabilities as well. So lower versions of the Android operating system can have more security vulnerabilities and allow for different types of attacks. So we had to be careful about what types of the operating system we're allowing our application to run on, because we want to have it run on the most secure possible without obviously isolating a lot of our customers. Also, the Linux kernel, as a side note, allows access to the physical components of the Linux device controlled by drivers, just like any device, right? you're going to have drivers for your different hardware components. And this is kind of where the hardware abstraction layer comes in, because the hardware abstraction layer allows applications to access hardware components irrespective of the device manufacturer or type. You can obviously imagine two different Android phones by two different manufacturers in the store side by side. Maybe they're the same price phone, right? But those phones all have different components inside of them. Maybe one has a camera made by one company, one has a Bluetooth sensor made by a different company, right? But the hardware abstraction layer allows our applications irrespective of the device manufacturer, irrespective of the components inside of it, to access things in generic categories like the camera, the microphone, the location, Bluetooth, touch drivers, etc. So our applications actually do not need to know any of the specific drivers for those hardware components or the manufacturer details. The hardware abstraction layer allows our application to access the microphone as the microphone, right? And doesn't care about who the manufacturer was. It just knows that's the microphone. So things to keep in mind here that are interesting, new and upcoming HAL types, such as automotive, right? A lot of phones these days have support for things like Android Auto and Apple CarPlay. That means that our phone is now interacting not only with itself or Bluetooth or 4G, but we're also interacting with our automobiles, right? We also have emerging categories such as IoT with things like fitness watches and fitness devices like Pelotons, where our devices might be tracking our heart rate monitor off of the Peloton. Also some integrations with our IoT home devices, so things like Alexa, Google Home, etc. Our phones are now interacting with those as well as a hardware component irrespective of the device manufacturer. Another thing to keep in mind that's going to be upcoming is going to be things like gaming peripherals. Maybe we're hooking controllers. You can even, in some cases, hook your phone up with a USB-C port and have it display things just like a normal computer. So things like gaming peripherals and interactions, when our phones become more like laptops is when we're going to see these new HAL types emerging, where phones and applications are going to need to start supporting even more additional peripherals. Okay, now we're going to talk about the native C versus the Android runtime. So when it comes to our Android device, C and C++ is the device's native language, and anything that goes through C and C++ does not require going through a virtual machine. Things like the WebKit, which is a built-in web browser for applications. Sometimes when you pull up a website in an application, it'll kind of pop up this iframe looking thing. That is what is considered the WebKit, and that does not run through the Android virtual machine. And we also have things like OpenMaxAL, OpenGLES, which are UI frameworks for displaying 2D and 3D models. So in some cases, some things like games or different applications can actually run UI frameworks through the device's native language. Now the thing is that Java is often easier to code in for many developers, so usually developers prefer this. Anything that is going through Java is going to go through the Android runtime environment. So older apps are usually built in strictly Java, while newer ones are built in this thing called Kotlin. If you don't know anything about Kotlin, definitely recommend looking into that as well. And in 2019, Google actually announced that Kotlin is going to be the preferred coding standard for Android applications in the future. And Kotlin is currently utilized by about 60% of professionally developed applications out there on the Play Store. If you want to read more about Kotlin, you can go to developer.android.com/Kotlin. We'll pop this open real quick. You can see, it has some documentation here about how to write things in Kotlin, how you can learn things from scratch. Definitely recommend going out there and learning that, because if you want to learn how to develop an application as well, it can be very helpful for you. Okay, now moving into the Java API framework, and this is really what allows your app to interact with other applications as well as the device itself. So in the Java API framework here, you can see we have things like content providers, which is a way of sharing data to other applications via a specific directory. Usually it's in this format, content, : / whatever the application URI is, / directory. And this is something we'll be looking for in our static analysis process to see if our application is sharing any data out there. The view system in the Java API framework is used for making the app's UI and normalizing it across the phone. We also have things for managers that are going to be running things in the background, such as our notifications. Maybe your application pops up a reminder when your appointment is due or you need to go and do something, right? Allows for telephony, making and receiving calls. Package management. Now this one is actually pretty important for applications because this manages looking for updates for our application as well as ensuring integrity of those updates. So if the application developer pushes out a new critical update to resolve some issues, this is what we would utilize to make that application actually update and go out and look for the updates. Also things like the location manager. This would get your fine and coarse grain locations for your application if you need location services for whatever the application is. Okay, and the last and final area of the Android architecture is the system applications layer. And this is where we're going to find our pre-installed applications on the Android phone. Generic things like our contacts, phone, system settings, text message apps, camera, etc. Also, something that has become very popular is that many Android phones come with some default Google applications installed, like Gmail, Google Settings, Google Maps, all that kind of stuff, right? So Google applications can kind of be considered a system application at this point, as well as many vendors such as Samsung, etc., have their own vendor-specific applications that are pre-installed on the phone. So these system applications are all what would be considered part of the system application layer that kind of come generically installed on every phone. Now the cool thing about Android obviously is that customizability, where you can always set up a new default app to replace a vendor supplied app or a system app if you don't like it. So just remember you can always go into those settings and change those default apps if you're looking for using things that are not part of the system application layer. Okay, so that wraps up our Android architecture. Hope you enjoyed the video, and let's get into the next one.